Okay, good day to all of you. So, in this video tutorial, you're going to learn how to do the deadlock detection algorithm. So, what you see now is the actual example from chapter 8 deadlocks. So, we're going to derive how does the sequence from here, this particular sequence, how did the solution has come up with this type of sequence. So, we're going to derive and show you how this is done. So, let's start. So again, we have 5 processes P sub 0 through P sub 4. Then we have 3 resource types. So A has a total of 7 instances, B is equals to 2 instances, and C is equal to 6 instances. So we have snapshot at time T sub 0. So we have 5 processes, and then they have their own allocation values, request values, particularly for A, B, and C, and we also have the available vector. So as you can remember, it is similar with the banker's algorithm. The only key difference between the two is that for banker's algorithm, they're using allocation and then max and then available. And then for deadlock detection, they're using the matrices allocation and then request, and then they also have this vector values available. So we already have an answer here. So this sequence, so P sub 0, P sub 2, P sub 3, P sub 1, P sub 4 will result in finish is equal to true for all I. So let's just show you will this sequence will finish the execution of all the processes. Okay, so let's start. So we will be indicating again the available. So available, so let me write. Okay, so for our available, and then we have resource A, resource B, and then resource C. Okay, so our available is 0, 0, 0. Okay, so based from the given request, okay, which of them can be granted? Actually, for the sequence, we have P sub 0. So let's choose P sub 0. So P sub 0, so what is its request? So just like with banker's algorithm, you're going to subtract the resource values. Okay, so we have the request resource values is 0, 0, 0. So we're going to write it as, okay, we have minus 0, 0, 0. Of course, 0 minus 0, it is all 0. Okay, then after P sub 0 has finished execution, so similar to banker's algorithm, you have to return all the allocated resource values that P sub 0 has acquired. So for this problem, so how are we going to return it? Actually, you have to add allocation plus request. Okay? Don't just return the request or the allocation. You should add allocation plus request. For banker's algorithm, it is equivalent to max. So okay, our allocation here is request, of course, is all 0. So our allocation is 0, 1, 0. So you have to return 0, 1, 0. Okay, then of course add. So we have 0, 1, 0. So we're already finished with P sub 0. So next is we have P sub 2. So P sub 2. Okay, so the request is also, it does not need any request. And then of course 0 minus 0, 0, 1 minus 0 is 1, 0 minus 0 is 0. And then next is we're going to return all the allocated resources of P sub 2, which is request plus allocation. So we have plus 3, 0, 3. Okay, then so 0 plus 3 is we have, of course, 3, 1 plus 0 is 1, and then 0 plus 3 is 3. Okay, So this is already our available, the current available resource values for A, B, and C. Okay, so next is, it is decided that it will be P sub 3. Okay, P sub 3. So P sub 3 is, the request is, we have to subtract it, 0, 1, 0, 0. So 3 minus 0 is 3, 1 minus 0 is 1, and then 3 minus 1 is, we have 2. Okay. Then we need to return the allocated values if P sub 3 has already finished execution. So let me rewrite again 2, 1, 3. Okay, so we have 2, 1, 3, and then P sub 3's to be returned is, we have to add. So 2 plus 1 is 3, then 1 plus 0, 1, 1 plus 0 is 1. So we have to return 3, 1, 1. Okay, so we have plus 3, 1, 1. So we have 4, then 1 plus 1 is 2, and then 2 plus 3 is, we have 5. So we already have 5, 2, 4. And then next to the sequence is P sub 1. So P sub 1's request is 202. So we have to deduct it again. So we have, rather P sub 1 rather. Okay, P sub 1. So P sub 1 is, okay, P sub 1 is 202. So minus 202. And then 4 minus 2 is 2. 2 minus 0 is 2. 5 minus 2 is 3. So we have 3, 2, 2. Then after that, we have to return the allocated resource values of P sub 1. So we have 200 plus 202. So 2 plus 2 is 4. 0 plus 0, 0. 0 plus 2 is, we have 2. So we have 402 in total. So we have plus 402. Okay, then 2 plus 2 is 4, then 2 plus 0 is 2, 3 plus 4 is, we have 7. Okay, next is, we have, so last but not the least in the sequence is, we have P sub 4. So let's write P sub 4. Okay, and then what's the request of P sub 4? So P sub 4 is 002. Okay, so we have minus 002. Okay, so 4 minus 2 is 2. 2 minus 0 is 2. And then 7 minus 0 is 7. And then next is, what we're going to do is, after P sub 4 has finished its execution, we have to return all the resource values. So 0, 02 plus 002 is, we have 0, 0, then 2 plus 2 is equal to 4. So plus 004. So we have 6, 2, and then 7. Okay, let's check. Since it is indicated in here that the total number of instances for resource A is 7, B is 2, and then C is equal to 6. So let's check 726. So 726, it means that the sequence of this process will not have the system in a deadlock state. So that's why in this statement, so sequence, so we have P sub 0, P sub 2, 3, 1, and 4 will result and finish, which is equal to true for all I. So all the processes has finished its execution. So this is example from the slide presentation. So again, the question is, can we still find another sequence that will satisfy that all of the processes will finish its execution? So as we can see with the with our example. So our request here is p sub 0 and p sub 2. What if we're going to instead of p sub 0, go first with p sub 2. So let's have another example for that. Okay, so let's start with again for our available. So available, okay, available. So we have A, B, and C, and then 0, 0, 0. Okay, again, instead of P sub 0, so let's go with P sub 2. Okay, so we have P sub 2. Okay, so minus the request. Okay, so we have 0, 0, 0. And then for P sub 2, let's return the allocated resource values after P sub 2 has finished execution. So let's return allocation plus request. So since this is all or 0, again, let's add it as 3, 0, 3. So the result will still be 3, 0, 3. Okay, so we're already finished with P sub 2. Okay, next. Okay, since our available is 303, as you can see here, our available is 303. Actually, we can already select any of the requests, rather any of the processes. But if you want, for example, of course, it's safer to select the smallest. But again, if it's already fits the values of the request is already it fits already with the available resources. So actually you can literally go with P sub 1 if you want to, because it already fits the available vector values. So but then again, as I've said, so let's just for example use P sub 0. So P sub 0, so the its request is also 0, 0, so 0, 0, 0, and then okay, nothing happens because P sub 0 does not request any resource. And then you have to return the all allocated resources plus of course allocation plus request, so plus 0, 1, 0, so we have 3, 1, 3. Okay, so next, what if I want is P sub 4? So P sub 4 is, the request is 0, 0, 2. So P sub 4, so minus 0, 0, 2. Okay. Going to deduct. Okay, so we have 3 minus 2 is 1, 1 minus 1 is 1 minus 0 is 1, and then 3 minus 0 is 3. And then next is we want to return the all the allocated resource values of P sub 4 after it has finished execution. So again, let me write this down. So we have 3, 1, 1 plus, so the total for P sub 4 is we have, okay, so 0, 0, 2 plus 2 is we have 0, 0, 4. 0, 0, 4. Okay, 1 plus 4 is 5. 1 and then 3. Okay, and then next, okay, we're already finished with, again with P sub 2, P sub 0, and P sub 4. So next is, okay, since it already fits all, so I'm going to select either P sub 1 or P sub 3. So let's select P sub 3. Okay, P sub 3. So P sub 3's request is 1, 0, 0. So deduct 1, 0, 0. So we have 5 minus 0 is 5. 1 minus 0 is 1. 3 minus 1 is 2. Okay, then I have to return the values of P sub, all the allocated resource values of P sub 3, which is, so 2 plus 1 is 3, 1 plus 0, 1, 1 plus 0 is 1, so we have 3, 1, 1, so plus 3, 1, 1, so we have 5 plus 1, 6, 1 plus 1, 2, 2 plus 3 is we have 5, and then we're already finished with P sub 3, and last but not the least is we have P sub 1. So its request is 202. So for P sub 1, deduct 202. Okay, so 6 minus 2 is 4, 2 minus 0 is 2, 5 minus 2 is 3. And then after we finish the execution of P sub 1, so return the allocation plus request all of its allocated resource values. So 2 plus 2 is 4, 0 plus 0 is 0, 0 plus 2 is equal to 2. So we're going to return is 402. So plus 402. So we have 4 plus 2 is 6, 2 plus 0 is 2, and then 3 plus 4 is 7. Again, let's check. So again, the total resources, A is 7, B is 2, and then C is 6. So again, we have reached the values, correct values, so it means that it is correct. So our conclusion here is that, so we can write the sequence. Okay, so the sequence P sub 2, P sub 0, P sub 4, P sub 3, and then P sub 1 will result in finish is equal to true for all I. For all I. So this means that the sequence, the processing of the sequence will not have a deadlock because all of the processes has already finished its execution. Okay, so there is another request. What if, for example, so next is what if P sub 2 requests, okay, so what if P sub 2 request additional resources, request, so we have 0, 0, 1, so it means that it wants to have additional request for C. Okay, so we have to change our request. Okay, so our request matrix. Okay, so request matrix. Okay, so we have A, B, and C. P sub 0, P sub 1, P sub 2, P sub 3, and P sub 4. So let's just copy the request for those that does not have any changes. For we have 0, 0, and then we have for P sub 1, it does not have any change. So for P sub 2, since the request is additional C instance, so see we have 0, 0, 1, so P sub 2 will become 0, 0, 1, and then we have P sub 3 is doesn't have any change, and then also P sub 4 0, 0, 2. Okay, so this will be our new matrix because there's a change in the values of P sub 2. Okay, still the available is 0, 0, 0. So the question now here is a question, what is the state of the system? So before we answer that, what is the state, is we have to again go with the algorithm. So let's write the available. So available is For A, B, and C is we have 0, 0. So which of these processes can be granted with the request? Actually, it's P sub, the only one with without any request from any other resources A, B, and C is what? Is P sub 0. So let's write P sub 0 and then deduct its request. So we have 0, 0, 0, and then nothing changes. Okay, so next, after we execute P sub 0, it should return all its allocated resource values. So add allocation plus request for P sub 0. So we have 0, 1, 0. So we have plus 0, 1, 0. And then 0 plus 0, 0, 0 plus 1 is 1, 0 plus 0 is 0. Okay. So let's check. Our available now is 0, 1, 0. So we're already finished with P sub 0. So which of the following processes will be executed next? Okay. Can we execute 2, 0, 2? Okay, actually we cannot execute because there is no available for resource A, for it needs 2 instances of resource A. It has an instance of B available for B, but P sub 1 does not need any B resource. And then just like with C, just like with A, C also needs 2 instances of resource C, but for the available, it is 0 or it's not available. So P sub 1 cannot be executed. Okay, can P sub 2 be granted its request? Actually, you cannot also grant it because as you can see with C, it needs 1 instance of resource C, but our available is 0 for resource C. Okay, so P sub 2 is also not possible. Okay, P sub 3. Can the request for P sub 3 can be granted? Actually, it's also a no. Why? Because it needs 1 instance of resource A. For available, there are no available resources for A. So again, this cannot be processed. And last but not the least is we have P sub 4. We have 0, 0, 2. So can this be, the request can be granted or not? Actually, it cannot also be granted because as you can see again, for resource C, it needs 2 instances and there is no available resource for C. So, what does this mean? So, what is the conclusion for this example? So, now the question is, we can already answer the state of the system. So, what is the state of the system? So, we can write the answer. So, deadlock exists. Okay, so consisting of, okay, since P sub 0 is the only process that has a finished execution, so you have to enumerate the processes that did not continue its execution because of lack of resources. So you have to enumerate consisting of processes P sub 1, P sub 2, P sub 3, and P sub 4. So for this example, if P sub 2 requests for additional resource for C, which is it needs 1, because of that request, there exists a deadlock. So consisting of course, processes P sub 1, 2, 3, and 4. Those processes that has not finished their execution. Actually, they didn't even started. Only P sub 0 has finished its execution. So again, if this is the case, so those processes that has not even started its execution, they have the deadlock situation. So I hope that you've learned something from our tutorial. So using deadlock detection algorithm. So if you do have any questions, so please feel free to comment below. And again, please don't forget to like my YouTube channel. So I hope that you've learned something with regards to the application of deadlock detection algorithm. So again, thank you very much and good day.